So what we want to look at today is how do we find the area between a non-negative curve, an axis, maybe two axes, or between two vertical line segments, or a vertical line segment if you're using the y-axis. So we're going to start with this. So this can be written in calculus as what's called a definite integral. And what we're going to do is we're going to bound it between what's called an upper sum and a lower sum. Now we're going to use technology to do this, and this is going to take us some time. So let me go ahead and bring this in. We're going to go to geogebra.org, and I'm going to use Classic. Org. It might help if I spell org right? Okay, and GeoGebra Classic. And I'm going to come here, and I'm going to name the function that's going to help me in a second. And you don't even have to make this a piecewise function, so I'm just going to put 16 minus x squared. Now, if you want to, you can get down out of the power, put a comma, and I'm just going to say I want to look at from -2. Okay, oops, don't forget the equal sign. Less than or equal to 4. Okay, and I'm going to drag this so we can see this. Now, there are two things that we're going to do. I start by typing upper. Now, click on upper sum. Since I named the function, notice how it's highlighted. Name of function. Where am I going to start? Let's say I didn't put what I put up there. I would just type I'm going to start at -2. I'm going to end at 4. And we're going to start with rectangles. So as you can see, an upper sum is an overestimate. Why? Look at all this excess area. Now I'm going to come over here. Let's see. I think I want the wrenched. Yes, that's what I want. I want to make sure I'm looking. This wrench. And I want 4 decimal places. There we go. And the other one we're going to want is lower sum of f. We're going to start at -1. We're going to end at 4. And I'm just going to put in one rectangle. And I'm going to turn upper sum off so you can see that, look, there's no area there. Now, here's what I want you to do. I want you to first stay with me. I want you to make a table of values. N will be the number of rectangles you're going to use. First, we're going to start with 1. Then we're going to do 2. Then we're going to do 3. 10. Okay. 25. 50. And we're just going to go up to 100. We actually could do more. And what I want you to do is I want you to record this for the lower sum of whatever rectangles and the upper sum. Now, a lot of people will use capital S sub n for upper sum, and a lot of people will use little s sub n. They used to use L's and U's, but then Riemann changed everything, and we'll talk more about that. But go ahead and look for patterns as you're doing this, and then unpause the video and let's check our answers. Okay, now you should have had time to complete your table. Now, I'm going to put something in here. I'm going to call this a slider n. N is going to represent the number of rectangles. Well, look, you really can't have 0 rectangles, but we will. And I'll put 250, and we'll count by ones. You're like, well, Mr. Isaac, that's not going to help. Well, watch what happens here. I'm just going to start. now both of these commands depend on the number of rectangles. I'm just going to start with the upper sum. Let me turn the lower sum off. And I'm going to pause it. Now look, as you add more rectangles, notice the widths are all the same. Notice they're non-overlapping. But the only way a computer can do this is to make the widths equal. As the number of rectangles continues to increase, the widths approach 0. The amount of extra area becomes very, very small. Now notice, we're only at 156 non-overlapping rectangles, and we only have 72 units of area. Now let me turn that off, and let me bring this here. And whoa, okay, hold on. I want to lower some. See, it doesn't like 0 because it's... Okay, here we go. Ready? Woohoo! Watch that fill in. Now that's only 50, and I'm at 70. So what happens? Well, let's take a look at our data table. Okay. Notice the lower sum is a sequence. Whoa, I hit the wrong button. I apologize. It's a sequence that's increasing as you add more and more rectangles. The upper sum is a sequence that's decreasing. So what's really happening is the true area is between these. And it ends up that the limit, we'll just call this f of x, is the limit as n goes to infinity of the summation of the rectangles 1 to n. Okay. But what is that? That is the summation from I equals 1 to n of a y value times a width. Now the width in each of these cases is right endpoint minus left endpoint by the number of non-overlapping subintervals. But those non-overlapping subintervals form, when you draw on your rectangles correctly, non-overlapping rectangles, and then you add your areas as you, and I always start from the left and go to the right. Okay, it just so happens we're going to use the squeeze theorem because the upper and the lower sum have the same limit. That's why these are equal. What's enough? If this limit exists, we say the function is integrable. Well, then Riemann came along, and Riemann found out that, hey, you don't have to use upper and lower sums. He began using left and right sums. So one of the things we really want to talk about today is the partition, when the widths are the same. So you have this width. Okay. You start, in our case, our left endpoint was -1 if my memory is correct. They're going to call that x naught. Why? Because I have no widths. And then x sub 1 will be the left endpoint plus 1 width. And x sub 2, now in general we write it this way. X sub 2 will be the left endpoint plus 2 widths. In general, it's the left endpoint plus 2 widths. Do you see this? Left endpoint plus a number of widths. Well, we keep going on, and we get to what's called the ith subinterval. And what happens there? We start at the left endpoint, and we add, we just look at the indices, and that's how many widths we add. So in the general partition, left endpoint plus, that'd be I minus 1 widths, left endpoint plus I widths, and we keep going till we get to what's called x sub n, which is -1 plus n widths. But the widths will be, which would be -1 plus 4, if my memory is correct, over n. Hey, look, the n's simplify, the -1s cancel out. Hey, guess what? We end at the right endpoint. So this is very, very robust. But Riemann came around and he found out this. How you pick these sample points doesn't matter. It used to be, it did matter, because you would look at this subinterval to set up your sum, because we add on I, j, and k as our indices. And he said, you know what? I don't need an upper sum. All I need is a sample point. No matter how I pick it, they're all going to collapse. They're all going to have the same limit. So what became important were left sums, right sums, and midpoint sums. Left endpoint, left sums, right endpoint, right sums, the average, the midpoint, midpoint sums. There's another type of partition. In that partition, all of the subintervals don't necessarily have the same width, but there will be one subinterval that is the biggest, the widest, and it's called the norm of the partition. And we just force the norm, the widest subinterval, to 0, because if the widest subinterval goes to 0, then they all go to 0. I mean, this is really, really robust. So what does it mean to be integrable? Well, if f, now by the way, integration theory is far more forgiving than derivatives, differentiation. One, if f is continuous on a closed interval, then it's integrable. What's that mean, Mr. Isaac? That means you can evaluate that. That also means that when you take the limit as n goes to infinity of the finite sum, it has a value, and that value is the value of this definite integral. In fact, a function doesn't even need to be strictly continuous. You can have wholly functions, removal discontinuities, and even step discontinuities as long as they're finite. Now, one thing I would like to talk to you, because now that you're older, so to speak, is if I gave you a function like this. Okay, Mr. Isaac's going to draw, so you gotta be forgiving here. Oh, wait a minute. Okay. This will be g of x, okay? And I want the area underneath g of x from 0 to 9. I do expect my young adults to remember their geometry. Oh, wait a second. Hey, Mr. Isaac, I see a triangle. So I would like you to say, hey, I'm going to integrate this from 0 to 6. And then I'm going to integrate this from 6 to 9. Okay. This area from 0 to 6 is a triangle. And if my memory is correct, the area of a triangle is 1/2 the base times the height. Hey, and this is a rectangle. That's the base. The base is 9 minus 6. I hope that's still 3. The height is 4. That's 18 and 12. And that's 30 square units. Now, what other kind of, quote, geometric shapes do I expect my young adults to be able to work with? Triangles, rectangles, squares, trapezoids. Okay, but break them up so that I can see that you know. Break this integral up. Now, Mr. Isaac, why can I do that? There's one reason why. What is the width of this interval? The width is 0. So the area that you're adding, because g of x is finite, but a finite number times 0 is 0. So whenever you see a continuous function integrated from any point to the same point, that's 0, and that is a property of the definite integral. Another property is if you have a definite integral from a to b of g of x and x, if c is an interior point, what's that mean, Mr. Isaac? C is between a and b, then you can split this into a sum of two definite integrals. Now, very quickly, we're going to go from just finding area to finding value. And you need to be very careful, because value of an integral is sometimes the same as area, but sometimes, quite often, they're different. Also, area under a curve has meaning. For example, let's say I give you a velocity curve in feet per second, and this is in seconds, and you have this, right? Let's think about this. When you take this rectangle here, that's a height, and we'll go from A to B. Okay. So this area from A to B of V of T in T. Okay. First of all, in this example that I've given you, V of T is non-negative, which means this is two things. It's total distance traveled from T equals A to T equals B seconds. It's also the displacement, the location from T equals A to T equals B seconds. Okay? So, but when you look at the area of this, if you think about it, your height is in feet per second, your widths are in seconds, so the seconds simplify. So you are accumulating feet. So the meaning of this integral is the displacement and or, under some opportunities, the total distance traveled. If velocity is non-negative, total distance traveled and displacement are the same. If the velocity is both negative and positive, then you can't get it. In general, if you want the total distance traveled, you're going to integrate the velocity function's absolute value on that closed interval. Now here's why. Let's say I give you a velocity curve that looks like this, right? Well, okay, I'm moving to the right, moving to the right. Oh, moving to the left, 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 left. By the way, that's a lot of area. That's more accumulated area than here. So I'm over to the left. Now I move to the right. So this is going to be your position, your displacement at the end of this time. Let's say we're going to go from 0 to B. Well, the way you find this, if you really, really think about it, there's two ways to do this. But the first way is if you take that negative area and you reflect it, just the negative area, over the x-axis, the time axis. We now are accumulating area, and now this is total distance traveled. That's why you'll often see people just integrate this in an abundance of paranoia to get total distance traveled. You are now in the heart of the matter. This is a very rich topic. I hope this helps.